In this section we will discuss mobile fading channels, and that is fading due to the motion of the station communicating with the access point or base station in the case of 802.16e. When a subscriber is in motion in a vehicle, the channel exhibits fading due to Doppler shift. As the vehicle approaches a base station, there is a Doppler shift and the frequency changes, and there is a spreading called the Doppler spread that results in fading in the time domain. That is, the envelope of the received carrier exhibits deep fades as a function of time. In this section we will actually derive the envelope of the fading as a function of the frequency of the carrier and the vehicle's speed. Fading due to Doppler shift is very detrimental to the communication system, and it has to be taken into consideration. Therefore, we will spend some time in deriving the power spectral density of the Doppler shift and the Doppler spread. Also, we will look at the time domain and the fading in the envelope. An excellent reference for this work is William Jake's Microwave Mobile Communications, which was published in 1975 and republished recently. We will derive the Doppler shift as a function of velocity, vehicle velocity, and carrier frequency. Here we show the base station transmitting a signal to a mobile. The base station transmits at a carrier frequency f sub c, and as the vehicle moves, the received signal at the antenna from the transmitter exhibits a phase shift as a function of time, and we will show this. For example, when the vehicle is in this position here, the distance from the base station antenna to the vehicle antenna is shown here. When the vehicle moves, the distance becomes smaller when it moves toward the base station, and we have a phase shift between the vehicle at this position and as it moves. The changing of phase over time results in a frequency shift, as we see in the definition of frequency as a derivative of phase divided by 2 pi. So the key to obtaining the resulting change in frequency due to Doppler shift is to derive an expression for the change in phase. If you look at the vehicle at this position here and at the position where it moves, we see that at a time delta t, the vehicle with velocity v will move a distance v delta t, which is this distance here, and delta x, which is the difference in distance between the two positions from the base station antenna, is equal to v delta t cosine theta, as shown over here. So delta x is equal to v delta t times cosine of theta. Next, we need to derive the phase shift corresponding to a difference in distance of delta x. And this is this expression over here. So the phase shift is equal to 2 pi over lambda times delta x. If the wave travels a distance of lambda, then the phase shift is 360 degrees. Therefore, a phase shift corresponding to a distance of delta x is equal to delta x times 2 pi over lambda. We can substitute for delta x this expression here, so we get 2 pi over lambda v delta t cosine of theta. If we divide both sides by delta t, we get the rate of change of phase is equal to 2 pi over lambda v cosine of theta. And the limit, as delta t becomes very small, we get the derivative of the phase shift is equal to 2 pi v cosine theta over lambda. And if we go to the definition of frequency, we obtain that the Doppler shift is equal to 1 over 2 pi, the rate of change of theta, the phase, which is equal to v over lambda cosine theta. Another useful form for the Doppler shift is obtained by replacing lambda by the speed of light divided by the carrier frequency f sub c, so we get the expression over here for the Doppler shift. From this expression we see that if the theta equals 0, that is if the transmit antenna was in direct path of the vehicle, we have the maximum Doppler shift, which is equal to f sub m equals to the velocity divided by the wavelength. Another point to consider is that the Doppler shift could be either positive or negative, so that the frequency, the carrier frequency that the vehicle receives is actually changing, either increasing as the vehicle moves toward the base station or decreasing as the vehicle moves away from the base station. This can be seen by this expression over here, where the frequency, the Doppler shift, is a function of the angle and is equal to the carrier frequency plus a frequency shift due to Doppler, where it can either be positive or negative, and therefore we get a Doppler shift around the carrier frequency and we have a spreading of the spectrum. Here we show the power spectral density due to Doppler shift, which we are going to derive in the following slides. However, we'll give you a preview at this point. Here we show the vehicle, and the vehicle receives plane waves from the base station arriving at different angles, say theta 1 or theta 2. Now, in an urban environment with many buildings and a base station, the actual transmitted signal from the base station is scattered by the multiple buildings and other structures such that the scattered waveforms arrive at the antenna of the vehicle at different angles. And we can assume that the arrival angles of the plane waves due to scattering from the base station, that these angles would arrive with a certain distribution. We will call that distribution piece of theta. So piece of theta is a probability density function for the angle of arrival of the plane waves. Now we can assume that the probability density function for the arrival of the angles is uniform. That is, there's equal probability for the signals to arrive from any angle between 0 and 360 degrees. If we assume a uniform probability density function, then of course piece of theta becomes equal to 1 over 2 pi. This is a pretty good assumption in a dense urban environment where the actual antenna does not have line of sight with the base station and receives signals from many different angles. We are going to derive the relationship for the power spectral density due to Doppler as expressed over here. We're going to go ahead and derive this expression in the following. So we are going to derive the power spectral density. First of all, we note that the Doppler shift is a function of the angle theta, which is the angle of the plane wave with the antenna. And that, as we derived, was equal to the carrier frequency plus the Doppler shift. The Doppler shift, of course, can be positive or negative with a maximum Doppler shift of f sub m. Also note that f of theta is an even function. So if we replace theta by minus theta, because of the cosine term, we get f of theta equals minus f of minus theta. And the maximum Doppler shift is the velocity divided by the wavelength. Now, if piece of theta is the probability density function of the arrival angle, then p theta times d theta is a fraction of the total incoming power within an angle of d theta. So if we go back to the antenna here, then within a small angle d theta, the probability density function of the angles times d theta would be the amount of power that is received within the small angle d theta. Now the antenna has a power gain of g sub theta, and antennas usually have a power gain which is a function of the angle. So the differential variation of the received power with angle would be equal to some constant b times g theta related to the power gain of the antenna times the probability density distribution of the angle itself times d theta. So this is the amount of power, or the variation of power, within a small angle d theta. Now at this point we're not going to make any assumptions on piece of theta as we did before. Now by definition of the power spectral density, we have that if we multiply the power spectral density times d sub f, which is equal to a small change in frequency, then that represents the amount of change of power. We set that equal to the amount of change in power due to an angle d theta. So the variation in power due to d theta is equal to the variation in power due to a small change in frequency df. Now if we go back to the previous expression, we know that the frequency is a function of the angle theta, and if we form the differential d sub f, we get that it's equal to f sub m times the magnitude of minus sine theta d theta, as we take the differential of the cosine term. And if we go back, we can actually express the sine of theta in terms of cosine of theta, and we arrive at this expression over here. We can write that cosine of theta equals to f of theta minus fc divided by fm, so cosine squared, we can obtain cosine squared, and of course sine squared is equal to 1 minus cosine squared, and we arrive at this expression over here. So d sub f is equal to this term times d sub theta. If we substitute for d sub theta in the expression here, then we get this relationship for the power spectral density, S of f. Now the power gain for a quarter wavelength vertical antenna is a constant equal to 1.5. We're assuming that all the angles have an equal probability distribution, uniform distribution, so that p sub theta equals 1 over 2 pi. If we substitute back into this equation over here, finally we obtain this expression here for the power spectral density due to Doppler shift. Notice that it is centered around the carrier frequency, and at the carrier frequency there's a shift of plus and minus f sub m. We are plotting the Doppler power spectral density against the frequency centered at the carrier frequency. So by 0 we mean the carrier frequency. So we have a positive shift and a negative shift with a maximum positive shift of f sub m and a maximum negative shift of minus f sub m. F sub m in this case is 100 hertz. Note that in the expression that when f minus f sub c is f sub m, then we get 1 minus 1, which is 0, so we get infinity. So we have infinity at the maximum Doppler shifts. It is instructive to look at some simulation results. These are simulation results of Doppler shift due to vehicle motion. In this case, we're plotting the power spectral density at a carrier frequency of 5 gigahertz and a vehicle speed of 12.5 meters per second. You can compute the maximum Doppler frequency, which is 200 hertz. You'll notice that the energy increases as we approach the maximum Doppler shift, and this is just in line with the power spectral density that was obtained mathematically. Also note that as we double the speed, the Doppler spread is also doubled, and we have a maximum Doppler shift of 400 hertz. You can also see that the density is increasing as we near the maximum Doppler shift, in line with the predictions of the theory. The derivation of the Doppler power spectral density is very important in terms of understanding the effects of Doppler on the signal. If we take a good look at the situation that we encounter with a mobile moving in a dense urban environment and exhibiting Doppler shift, we noted that the vehicle's antenna receives plane waves from the transmitter at carrier frequency f sub c, arriving at different angles, and you have a large number of such plane waves arriving at the antenna and combining constructively and destructively. The signal at the receiver therefore can be modeled using the central limit theorem. In the central limit theorem, when you have a number of signals that are added to each other, then their probability distribution function approaches a normal distribution function or a Gaussian distribution function. So the signal that arrives at the antenna is approaching a narrow-band Gaussian random process. So this is due to the central limit theorem. However, the narrow-band Gaussian random process has a power spectral density shown here. So the narrow-band Gaussian random process centered around the carrier frequency has a power spectral density as expressed by this expression here that we derived, and exhibits a Doppler spread. But in the time domain, it is represented by a narrow-band Gaussian random process, which we will investigate next. In order to further study the effects of Doppler on the received signals, let's consider a narrow-band Gaussian random process. For a narrowband Gaussian random process centered around a carrier frequency of f sub c, it could be modeled as the summation of a in-phase term and a quadrature phase term where the amplitudes are Gaussian random variables. So Tc of t, which is for the cosine term, and T sub s of t, which is for the sine term, are zero mean random Gaussian variables, and they are uncorrelated. So T sub c and T sub s are uncorrelated, as we show here with the left and right greater and equal signs denoting expectation. The variance are both equal to e sub 0 squared divided by 2. The random processes Tc of t and Ts of t are both normal Gaussian random variables, and their probability density function is expressed by the following expression here, which is your well-known normal distribution with zero mean, and b is the variance. Here is a simulation result where we're actually simulating a vehicle moving at 50 meters per second with a transmit carrier frequency of 5 gigahertz. And we're looking at one of the processes, Tc of t for example, the in-phase component. This is the actual histogram of the simulation where we're actually simulating multiple plane waves that are exhibiting Doppler shift and being received by the vehicle's antenna through a multipath scattering environment. This curve here shows the actual normal distribution, so we see that the actual model is quite correct in the sense that the Doppler shift does represent a narrowband Gaussian random process. Now if we go back to the modeling of a narrowband Gaussian random process centered on a carrier frequency fc of t, if we demodulate this process with quadrature demodulation centered at the carrier frequency f sub c, we will recover the in-phase term and the quadrature phase term. And if we take those and compute their envelope, go through an envelope detector, then we get that the envelope is equal to the following expression. Now the envelope of two independent Gaussian random processes is actually well known. It is the Rayleigh distribution, and its probability density function P sub r is shown over here. And of course, since it's a envelope, it's only valid for r greater or equal to 0, and it's equal to 0 for r less than 0. Here we actually show the Rayleigh distribution and the actual histogram of the envelope of the Doppler shift when we have a carrier exhibiting Doppler shift for a vehicle in motion, in this case 50 meters per second at 5 gigahertz. So let's examine fading due to motion. Let's examine what happens in the time domain as you have fading due to Doppler shift. In the case here, we're actually plotting the envelope of the carrier, demodulated carrier, with a vehicle moving at 10 meters per second. So as the transmitter sends a carrier at 5 gigahertz, and we measure its envelope in the vehicle as it moves, we get, as a function of time, an envelope that varies with time as shown in this actual simulation. We see that there are many deep fades as a function of time. So Doppler shift does cause quite a bit of problem in mobile communications. So we have to come up with ways for combating the fading due to Doppler shift in a mobile wireless communication system. Let's compute a few parameters. Our vehicle speed is 10 meters per second and our carrier is at 5 gigahertz. Therefore, we can compute the maximum Doppler shift, which is 167 hertz. The inverse of the Doppler shift, the maximum Doppler shift, is called the coherence time, and that's equal to 6 milliseconds. And that's sort of the time frame through which we have fading. If we are sending a packet which is greater than 6 milliseconds, then the packet will exhibit major fading and it is not stationary. For example, in OFDM, if we sent a long packet, it would change over time so that any channel equalization that was done during acquisition would be invalid during the duration of the packet due to vehicle motion. And you would have to use pilot tracking in order to make the appropriate corrections. If we take the speed and half it to 5 meters per second, we get the following envelope as a function of time. And notice that it is not as severe as the case when the vehicle was moving at twice the speed. In this case, the Doppler shift is 83.3 Hertz and the coherence time is 12 milliseconds. What this means is that if we were sending a packet, the packet will not substantially change if its length was much less than 12 milliseconds. But if the packet exceeded 12 milliseconds, then it would exhibit fading, and we can have pretty much deep fades. Here we show the results of the envelope at 5 gigahertz with a vehicle speed of 1 meters per second, or in this case it is a pedestrian speed. The Doppler shift is 16.7 hertz and the coherence time is 60 milliseconds, which translates to the fact that if the packet is much smaller than 60 milliseconds, then it won't substantially change over time. And this is what you might expect to see in an office environment with somebody moving around with their power book. There are a couple of parameters that can be computed for a vehicle that is moving and we have fading due to Doppler shift. One of those parameters is the expected rate at which the envelope crosses a specific or a specified level r in a positive direction. If you look at the case where we're moving at 5 meters per second versus the case where we're moving at 10 meters per second, if we set a level at this point here, we see that the number of crossings of this level for the vehicle moving at 10 meters per second is much larger than the case for 5 meters per second. And the expected rate at which you cross the level is expressed by this expression here. And notice that this expression, actually, if you plot it, you get an interesting result. What I want to point out is that it is directly proportional to the Doppler shift. So the larger the Doppler shift, the more the expected rate at which the envelope crosses a level, as shown in these two diagrams. But this is an important parameter that you can actually compute. Another parameter is the duration of fades. So in this case, we're looking at the average duration of a fade below a level R, capital R. So if you have a level, for example here, you're interested in how long you are below that level during a fade. In this case here, we're at 5 meters per second versus the case we're at 1 meters per second. You will notice that during the case where we're moving slower, we spend more time below a certain level than in the case where we're moving at a higher velocity. Of course, you actually have to plot this as a function of the parameter rho, which is the ratio of the level divided by the RMS of the level, to really see the various regions. We've mentioned coherence time, but it's a very important parameter in dealing with mobile communications. So we saw that due to Doppler shift in a mobile communication environment where the mobile is moving at a velocity, high velocity, that you will get a Doppler spread, B sub d, which range from minus f sub m to plus f sub m, where fm was the Doppler shift. The coherence time is defined as the inverse of the Doppler shift, the maximum Doppler shift. And the key point on coherence time is that if you're doing packet communications, that the packet length, the duration of the packet, has to be much less than the coherence time in a good design. But there's ways of actually combating Doppler shift through tracking of pilots. But in general, this is a good design parameter. We should always assume that if the packet length is greater than the coherence time, then it will change, and if we had equalization during acquisition, we have to readjust due to the changes in the channel due to Doppler fading. Here we can highlight that point. In this figure over here, we're looking at the envelope at 5 gigahertz carrier and at a vehicle speed of 5 meters per second. The Doppler shift is 83.3 hertz. That's the Doppler spread. And the coherence time is the inverse, which is 12 milliseconds. So we're seeing that over time frames of 12 milliseconds, the channel changes and we exhibit deep fades. In the case that we're moving at a vehicle speed or pedestrian speed of 1 meters per second, we'll note that the coherence time is 60 milliseconds, so the channel doesn't change over a time period of around 60 milliseconds. So in this case, we can afford to send larger packets, whereas in the case where the vehicle speed was 5 meters per second, we have to actually use packets with shorter length.